All right, let's get started. Welcome to our first Harvard Data Science Initiative Industry Seminar of 2024. I'm Jen Chow, I'm Director of External Engagement, and it is my pleasure to introduce today's speaker, Praveen Pankajakshan from Cropin. Praveen is VP for Data Science and AI at Cropin, a global ag ecosystem intelligence provider that uses AI, ML, and remote sensing to create an interconnected data platform to transform agricultural operations. He's an expert in the theory and application of statistical signaling and image processing, pattern recognition, and machine learning across many industries, including energy, healthcare, and life sciences and agriculture, including time spent at Corteva Agriscience, Shell, and Samsung. Praveen received his PhD advised by Josiane Zarubia at Ariana, a joint project of INRIA and CNRS in France. We're thrilled to have him with us today. Before I hand over to Praveen, I'd like to remind our audience that there will be time after his presentation for questions. Audience members should use the Q&A function to send in their questions at any point during the presentation. Please don't be shy. All questions are good questions. All right, thanks and welcome, Praveen.
Thank you, Jennifer. Thank you, everyone. I'll first start by my introduction. So, as Jennifer mentioned, I'm part of Cropin. I lead the Cropin AI lab, and my background is machine learning. And I've been working in this field for about 20 years with various applications. I also wear a dual hat of visiting faculty in Amrita University. So, in this presentation, I'll try to wear my kind of like academic hat and also an industry hat. So kind of like shuttle between both of them. This is a work that, we have been doing in Cropin. And I thought that this might be looking at the current scenario of what's happening across the globe. This is something which also is very close to my heart. When I started off this journey with agriculture is about 7 years back. But my relationship with agriculture goes much longer than that, is that I also am a farmer. I have my own little piece of land. Unlike in, many other geographies, in India, for example, the bulk of the land is mostly very small, typically about an acre and a half. So that's usually very common. And this is also true in other geographies other than India as well, right? So a lot of focus actually of Cropin has been in working on these small landholding farms, right? And when we look at it from serving largely like underrepresented in terms of data and solutions also, which is available for that particular kind of farms, it's very limited across the globe, right? So we have actually taken on a very difficult journey, and it's these geographies which are primarily affected by climate and the influence of climate. And obviously it has large implications also on food security and how food is produced, and also indirectly also on climate itself, right? I would like to kind of argue that while there are many technology advancements, satellite imaging is one of the major tool to still do this at scale, right? So hence this topic of geospatial AI. So three things coming together: agriculture, satellite imagery, and AI. So this is a triangulation of these three areas, right? So I'll start a little bit with Cropin and then quickly move on to the next subject, to the main subject, sorry. So Cropin started with actually the digital transformation of agricultural lands. And what it means is that, many of farmers, they have their own lands, but they don't have, these lands are not geolocalized and geotagged, or, they don't have geoboundaries, right? So the first thing that we did is actually going around and drawing those boundaries across these different farms, right? So, and bringing that in-house, right? And then obviously the next question is, once you bring that, then what is it to do on top of it? So we build the intelligence on top of that. And then we looked at growing to newer geographies. We started with India, but quickly expanded to newer geographies and locations. And it led to the formation of Cropin AI Lab to build intelligence on top of all this data that we're accumulating. So when we talk about digitization of farmland, so we not only collect these field polygons, but also what kind of crop is growing, what's the sowing date, harvesting date, and any variety or any other information that goes along with it, right? So these are all anonymized and then made available for training the data, training the model. And and last year we released the first intelligent agriculture cloud to provide with solutions, right? Layered with multiple different options, right? And what is actually on the cloud? So all our solutions are actually built on the cloud. And so, and AWS is one of our partner from very early stages doing this. So, as I said before, when we actually engage with farmers, we bring their geo boundaries, and then we bring also along with it the different types of data that they have. Sometimes it might be soil moisture data, it might be temperature data, it might be soil temperature, or other things which are in situ or from data which is sometimes connected with some IoT devices and things like that. Or sometimes it might be lab data, right? Soil analysis data and things like that. So all of that comes into our system, right? And those are all used to build the intelligence on top of it. And then we also provide, the application layer for this, right? So that's the three different layers I was talking about. Over a period of time, we have actually served different kinds of applications itself. So when actually the farmers are onboarded into the systems, they are looking at end to end. So you have to understand that a farmer comes right from the time when they are interested, the intent itself is there of sowing in their farm the seeds, and then until the end harvesting, and in between monitoring it, right? How much of what's the nutrient that is content that should go into the soil, and how much of it is available for the crop. What's the kind of water usage that I should look at? What are the possible diseases that I could have? That we provide the early warning systems, and we also look at the current crop conditions and provide yield estimations and things that. We have also had other kinds of applications which are either related to carbon or management practices, and derivatives of that, right? So that's the gamut of things that we have actually served. In fact, we have served for multiple different countries. So usually what happens is farmers, farmer organizations or enterprises work with farmers are actually onboarded, and these services, or sometimes even governments, are provided with these intelligence and advisories. Um, so that's a little bit about the background, and I already talked about what my team itself does, and I want to quickly talk about climate smart agriculture. So I would actually argue that the earlier model of agriculture that we are conventionally used to, right? When everyone thinks about model, the first things, depending on the geography in which you're placed, you would either think about a tractor or a harvester, or even sometimes people think of drones flying in, right? Application of fertilizer or pesticides or whatever. Or it could be, a humble farmer going, plowing the field with his bullocks and things like that. So, the paradigm of agriculture that we are currently facing is based on either the traditional knowledge or recent advancements that you see, right? Actually, my argument is that that paradigm is slowly has to change, and it is changing. The landscape of the whole perspective on agriculture is changing, and I'll kind of give indications on how that is changing and why it's important for the planet. There are actually two reasons why we are doing this exercise. Is food security is one thing, but agriculture itself is responsible for a large amount of greenhouse gas emissions, right? Like, so if we do this right, in fact, it can be actually not only reduction in greenhouse gases, but uh, the food production itself can become a larger sink of carbon itself. If you look at the above ground biomass, the total biomass in the stock of the crop or in the soil, right? In fact, some of our collaborators, work only on soil, the capacity, improving the capacity of the soil to absorb the atmospheric carbon dioxide or atmospheric carbon, right? So there is a lot of benefit also in doing. So there's two benefits, right? One is providing food for a growing population, and the other is also providing, food in a sustainable, regenerative way, right? So, and not only that, the climate is also changing, right? And as climate changes, and you will see later on that I'll also provide supporting evidences from our own work that, the way that we have been traditionally farming should also change, right? Our climate is changing, hence sowing patterns change. When the kind of crop that is grown in a particular region change, the water usage changes, everything, right? So I took this particular, the sub-Saharan region as an example, as a case study, but I would also later on show that how this same work could be extended to regions in the rest of the world as well, right? For this kind of discussion, I took like two regions, two countries, Nigeria and Kenya, and two actually seasons in each country. But I'll have only time to show the one season in a country, right? So in Kenya, for example, we chose maize, and Nigeria, we took paddy as a major crop of interest. And the duration that the seasons that we take in Kenya is a short rainy season and the long rainy season for the study. And for Nigeria, it's the dry season and the wet season. Okay, so the corresponding seasonal times is actually given also right here. Now, if you look at the Africa as a continent itself, like it has like multiple different agroecological zones, right? What we mean by agroecological zones, and it's very, very diverse, right? Going from the north to the south, east to west, In fact, like many organizations actually classify based on the different climatic conditions, soil conditions, the availability of forests and other natural resources, they look at different agroecological zones. And within each agroecological zones, there can be multiple different climatic and weather conditions also, right? So you can see, for example, here in Nigeria, this is from the United Nations FAO organization. You can see that, there are, from the north to south, if you see, there are variations in, and in the climatic conditions itself, and you see that it goes from the Sahel Savannah region to almost the lowland rainforest area, so that's the kind of like diversity and, so even the mangrove forest, right? Similarly, like you can look at Kenya also. Kenya is also divided into, for example, you see these regions, and I'll talk a little bit about this, is that it's very arid to some of these zone ones, which are humid regions, right? So, and some of these are actually major maize growing regions, right? So this is a classification that's done. But what is happening is, and I'll give you indicators for this, is that these have been classified looking at 30-year time intervals, right? Most people look at 30-year time intervals. But even that is changing, with the temperatures rising and rainfall patterns changing. the main thing that we see is that these climatic zones are also shifting, right? So earlier, for example, this particular region is known to be very conducive for maize growth, right, in Kenya. Now, we were even seeing that, because of the change in patterns, farmer behavior is also changing, So I'll not give it out right now because I want to hold on to the data, but those are things which are evolving, right? So these are not, earlier it used to be fixed in time in a kind of way, but now these are also evolving, right? That means your growing conditions and seasonal change, seasonalities and everything is changing. Okay. The other thing is, like, I also want to give an idea of the aridity index, So this is especially the agricultural aridity index. So this is looking at, the how much of rainfall is available in a particular region and looking at the evapotranspiration that happens, evaporation and transpiration. That means the water loss that happens in the soil or in the crop, right? So you can see that some of these regions of Nigeria and Kenya, you can have extreme stress regions versus, some regions with minimal or no stress, So this is, like calculated recently. And you can also see that so there are possible simulations, climatic simulations that you can do, in which you can look at, for example, in 2030 or 2050, how does it look like, how does the aridity index itself look like, how much the rainfall is there and how much of evapotranspiration can be there, So that's also, we are also seeing that regions earlier, which was no stress or minimal stress, is actually moving to moderate stresses, to severe stresses, to sometimes from severe stresses to extreme stresses also. Okay. So these are, so I'll just give you, so those were just the inspiration elements. So now I come to how are we doing the monitoring aspect of it, right? So we use actually, we use data from multiple different sources, and it's not only like, so we have our own internal database. So I mentioned about where we go and collect, from farmers and across the globe, we geotag the data. So that's the geotags of plot level data, right? And we have like crop information, we have like yield information and many other things, management practices and everything. We then combine that with satellite data. We use both optical and radar data, and we use also Landsat data, there's thermal bands also. And weather conditions, not only the current weather conditions, but we can also look at past ones, as I said, 30-year climatical values and rainfall, right? So these are the different sources that we take from, right? And that's why it's multimodal in nature, because providing for, insights into growing regions is quite challenging, So I'll just give you a glimpse about what we mean by some of these data itself, right? Like weather data is obvious, right? So optical data is like similar to what you would actually use in your phone camera or some of your regular cameras, except you can imagine that in your phone cameras, you have like red, green, and blue, but you have like much more channels, we call it as channels than just that, So sometimes you have 13 bands, 13 channels, okay? So you can look at red, green, and blue and variations of that, right? You can have variations of red itself, right? Sometimes you have variations of yellow or variations of blue, Um, so that's what we mean by the optical band, right? And what we mean by SAR is, or radar, you will see me using that term as well, is, sometimes it's not, it's in a different, the electromagnetic wave spectrum, it's in a different range. And you're looking at the backscatter coefficients, like optical data, as you have the sun's radiations coming and you have your reflections here. It's a radar wave and it's a backscatter that we are looking at, right? But I'll not go into the details of this. So, so this is just for FYI as information, I'll go a little bit into these details, but this is the overall framework, how we approach the problem, right? Like, it's a busy slide, but allow me to kind of like walk you through that as well. Yeah, I see that there is, okay. Um, just checking if was there any question or not, but if I will probably address the question. I saw that there was one question, but I'll address that. So we take the satellite data, and what we do is we look at the input, the data that we get from our own field, collections. And then we get some derived parameters from it. We have to process the satellite data, and you have to understand that you have to overlap the information that is there in the smart farm on top of the satellite data. Sorry, the information which is there in the polygonal data on top of the satellite data. And then, we derive insights from it, right? So that's a processing thing. Apart from it, we look at from the satellite data, from the weather data itself, we look at, for example, how much of evapotranspiration could happen, right? And this is purely from a weather perspective alone. And then we do, on top of the satellite data, we do crop detection, and we get the crop maps, and then we estimate the yield. But there is something called this crop cutting experiment. So we go in the field and, select specific regions, and we collect, we kind of like physically go and cut the biomass that we are interested in of the crop. We weigh them, and, we use that as information to fine tune and validate our model, either fine tune or validate, right? So, and then we get the reports out for different administrative boundaries, right? Administrative locations. Now, what I want to mention also is that the data itself that we are getting, right? So that's with respect to, until now, what I was talking about is, you have the collection of the data, right? So all of that is put in a proper framework, right? Because we have been in this particular industry for 10 years now. So we have like apps which can go and which can be used for collecting the data. In fact, it's very simple for farmer to walk around his field and, like geotag, draw the polygon boundaries as well, right? All of that, when it comes into our database, I just want to give you an idea of how much of data, sample data we have. It's from 114 countries. It's about 15 million acres. Out of this, about 2.3 million plots are actually audited. Audited means like somebody goes and verifies that, right? And the total number of crops that we have as of at least, for 1,000 different kinds of crops, unique crops, right? And different, even within the crops, there is a lot of diversity, right? Agriculture has a lot of diversity, you must understand. It's not, as people might imagine, there is soil variations, there's crop variations, there's climatic condition variations, weather variations, right? Multiple different things, and the variety, that means the genetics of the crops is also could be very different, right? And then we have about more than 17,000 different crop varieties, right, for crops of these 1,000 crops, Now, the reason why I put this is that also, so we talked about the importance of, about how we collect the data, we talk about the framework, but, I'm told that the audience here also would like to understand about, about what kind of problems and challenges which we face. One thing that, somebody might ask, in the age of foundation models, do you still need so much amount of data, right? What we have seen is that even when we take minimal amount of this data, and we have done some selective experiments, and you can actually read a little about this, is that unlike like in academic problems where you actually like just build a model, you take the data, split into train, test, validation, and do some training on it and deploy it and infer on, the training and on the test or the validation set. And then you have your accuracy metrics, right? What we have seen is when we take a model from development to production, we face all these different problems, There are often like drifts, right? So when you select a particular set of data and when you only work on that, all of this can actually happen, right? Data drifts can happen, domain drifts, concept drifts, model drifts, because even as human beings, the way that we actually build models is inherently biased, so you can have actually those biases, unfortunately, coming into the data itself. We have seen, for example, in recent cases, how AI systems can be biased purely because of, how the data is, and the data in term has been collected by people, right? So that's why I would like to argue that it's very important. I mean, when you're talking about, if this group of people would like to talk about, about foundation models or about the next generation of AI systems, then I would argue that still diversity of data is very, very critical, right? That's why we ensure that, we want to actually even, I'm not even sure if, and these are countries which where often it's really underrepresented, right? Where you don't have so much amount of diversity of data in other either publicly or private data sources, right? So it's very easy to build systems and based on data which is there, but often that data is often biased, right? So that's why diversity is important, more than anything else. Like, earlier it was, last generation was a generation of big data and everything. I would say that variety of data is more important, right? Um, so you can read a lot about at least detecting data drifts and how you can do it. And I'll give you some ideas of how we did that also. Okay. So this is one thing, one study that I did with, some of my colleagues. In fact, in India itself, I talked about Kenya, right? This is giving India, we took like data samples within India, and we actually found that, there are different zones, right? We know that there are different zones, but we now decided to collect data, I mean, group the data. We already had data, but group them based on the different zones itself, and what's the diversity difference between them, right? And there is, like, in fact, like you would expect that maize growing in one region is the same as maize growing in another region, but unfortunately, we found that that's not the case, right? So all the more reason for this, creating diversity, right? This is a very simple example. This is how, your chickpea and maize looks on a time series representation, okay? So when, I talked about downloading all of that satellite data, so we just downloaded that and created time series representations of that. So this is just taking like one single, it's an extracted feature from that, and we look at it from a temporal direction, because satellite image, when we look at from Google image or something, it's one single snapshot. But for agriculture use case, there is one more complexity to it. We are not only looking at the different kinds of channels, the spectral information, but we are also looking at the temporal also, and that's actually a key feature, right? So what we actually notice is that, even for chickpea, like often, depending on where we actually pick those zones from, right? We found that the crop signature, this, we call this as the internal crop specific spectral signatures that we have been creating in the spectral libraries. There is diversity, there is a difference in them, right? You can see that the amplitude is higher than the train and validation test, the set that we had in comparison to the test, Um, DAS means days after sowing. So you have like, here is the sowing and this is the harvesting, this is the maturity, right? Similarly for maize as well, right? So all this is very important to know, because it's not just simply a question of splitting your data set into 70, 20, 30 or whatever split, right? And doing the training testing on it. I'll not go into the details of this, but this is very well known, is that the way that we were looking at it is, can you actually take the data set, the temporal, including the temporal information? We already know like what that satellite data corresponds to. So we download the satellite data, we know that that particular plot is growing which crop, right? And we are trying to see like, so we now have a manifold representation. So this is a kind of like 2D representation of that entire cube, which is changing over a period of time, right? So you can imagine that it's very difficult to study that, right? So we need to represent it in a format which we can visually represent and understand, and it's also very important for us to understand which are the crops which actually have some differences and why do they have that differences, right? Like, so it's not simply a question of building models to differentiate between crops and everything, right? But it goes much beyond that, so you see that based on the scatter plot that we have in this representation, you can actually find these are the four major crops that we took. There's also one more crop in this, but these are some of the major crops of the world as well. You can see that there is separation, but you can also see that there is the groups are not like actually together sometimes. And we wanted to, and this is another representation of the same thing. That the earlier one was based on the crops that were going. This is based on the sowing date. We also wanted to understand, is there any difference between the sowing months, and the sowing season and everything, So sometimes what happens is like certain months become very dominant, in the sowing season. So you see that, for example, for this particular region, you have a lot of sowing happening in January and also in the later months after 8 months or so. So this is very typical. So we were trying to see if there is whether crop differentiation is there, whether sowing differentiation is there, and things like that. Now, interesting thing that we found is that if you look at, for example, just choosing one crop, paddy cluster alone, they cluster like in three different places, So we wanted to understand why do they actually cluster in three different places. And because they're crop signatures, so looking at each one of these plots, we see that their individual patterns and signatures, what I talked about, is much different. For example, what I'll just kind of explain to you what's happening here. Just look at the top one, for example. These are all the same paddy crops, but what's happening is like you can actually see that this this bell curve that's going up and down, this crest and trough. So that's actually like paddy crop being sown, and it's coming to the peak of the maturity and then getting harvested. And then the next cycle actually starts. So this is from the previous season, this is the current season, and the next season, right? Uh, so, so the only difference between these both is because this cycle is much longer, so this is probably a different crop which is coming, or this one where the farmer decided to keep it barren, right? So there's no crop growing or some other, short duration crop growing, right? So that's what is actually causing all these differences, right? So it's very important that to understand that, to know also how your models should, how your models and how your data should be trained, right? So, when you look at any satellite data, right? Like, so that's with respect to data itself, right? Like the ground truth data that you actually collect now. So it's very important to understand drifts which can happen in that. When you build models on top of it. Now, any data, any satellite data that you look at, now, when you think of a satellite data, you're probably thinking about the Google satellite map that you use for navigation, everything, right? The maps that the satellite data that we use is much lower resolution than that. That's higher resolution, and it's not often updated, right? Like this is much lower resolution. For us, the one of the critical element to know is that it's always changing, like a very simple thing is that there could be, for example, in a typical scenario, you could have, for example, suddenly a building coming up, right? And so, a satellite map, which was earlier barren, suddenly a building has come up, for example, in the previous use case, there was something growing and the farmer decided to keep it barren, right? So you see the usage of the land is changing all the time, What we built internally is also not like just static maps, but we built dynamic maps of, how the land is usage happens, And in fact, in agricultural land, it's always dynamic. It's never a static map. It's not like, today, like this farmer is growing this particular crop, so he has used this. But sometimes that farmer might decide only to use part of the land, or or might extend it to larger other parts of his land. So even the extent of the land is changing all the time, right? And that's why we don't want to rely on static maps. There are static maps, but we built our own maps, And this is one thing which you'll also see from some of the chat GPTs and everything, recently, is this idea of bringing human in the loop, right? So either you build it through reinforcement learning, or recently there's been a few other optimization techniques. But for this particular use case, what we did is we just did something called active learning. And what is active learning is that you build like baseline classification maps, of which areas, for example, all of this, like except the pinkish areas and everything, it's agricultural land, and it's evolving, so sometimes land, you see that the crop is from the previous season is still not yet harvested. Sometimes the farmer is early sowing, late sowing, late harvesting, early harvesting, all of that can happen, So we build the classification model initially. Then what we do is we use subject matter experts to kind of like find out which of those are actually like correct, which are not, we kind of then retrain the model. And then we provide the active vegetation cover. We call it active vegetation cover because it's really is the current season, what's happening of the land, right? So this is something first important thing to do, right? Before, when you get a satellite image, it's important to know which are the regions where you actually have an active vegetation map, across the globe, right? And it's a very, very hard problem. It's not an easy problem as it seems like, because do you consider a mango orchard as an agriculture area, or do you consider it as a tree, So those are decisions that you have to make, right? Do you consider palm growing areas as a tree? Do you consider coffee plantations as still as agriculture areas, right? Sugarcane plantations and things like that. So, it's a dynamic process. It's, as new use cases evolve, it has to like change continuously, right? All of these things that we develop is not for one particular region alone. We have used this as a case study for Kenya and Nigeria, and even, I'm going to show extensions to other geographies as well, but it can be potentially also put in South America, right? Or other regions of the world, right? So I'll show also some inspiring things also for the Americas, right? So so this is how, like, for example, as I said, it's a dynamic process. This is how, for example, this is actually an whole of the style is actually an agricultural area, but only parts of it has been used by farmers, so the rest of it is actually kept barren. Only the ones which is yellow is where there's an active crop, and sometimes for the farmer, for X or Y reason, they might decide not to have done sowing in some region. Some of them could just be like some farmhouse which they have, right? Like often you see that farmers have like small dwelling places also. It might not be, it might, or a shed and things like that, right? For storage, granary and things like that. So those are all excluded, right? And then on top of it, we run our crop masks. We identify which crop is growing in that region. So for example, here we have shown sugarcane versus maize, right? But you can have like other crops as well. Okay. One interesting thing is that I want to mention is this is a giant work that we're doing with a professor here in Indian Institute of Technology, Bombay. And one of our key, the thing that we bring to the table is when you actually also start about like data, right? And you have like, let's say, large data or minimal amount of data, because I've also worked on minimal amount of data. It's very, very important to, if you, for example, only use data-driven approaches, right? There are challenges with that, is that data-driven approaches, you will have like these data drift issues, uncertainties of the data, noise of the data will also come in and everything. So it's very important to bring in subject matter expert knowledge also into the system, or try to bring, so there is also some, new emerging ideas on making it explainable and everything, So when you bring models to production, sometimes, I had to, given a choice that I have to make, sometimes it's better to actually bring models to production which are explainable, and sometimes simple models, And there is no, sometimes there is no, simple models sometimes perform reliably well. They might not be very, very accurate, right? But the reliability and transparency and trust is much more important, right? So this is one such model which we built where it's really using subject matter expert knowledge. And here it's very simple, right? I would not go into the details of the whole satellite data that is being used. This is based on radar data. And this is for paddy, but I just put this because of saying that how important knowledge itself can become into bringing difference to your models. Injecting more knowledge into model becomes even more appropriate and relevant in the current scenario where, your chat GPTs and everything have started hallucinating, right? Even I'm saying chat GPT, but, I'm referring to language foundation models. Excuse me for saying that, but I'm not like specifically saying only about chat GPT, but I'm talking about large foundation models, language models, or vision models, right? They are known to have hallucinations, right? So the next set of research and models are also going to be in knowledge injection, right? So that's a key factor. So here, for example, the knowledge that is being injected is how the management practice of paddy cultivation itself. So paddy world over, they flood the field. They transplant the rice, they bring it from the nursery, put it in the soil, and they flood it, right? And that can be used. So that flooding is actually visible from the satellite data using radar data. So that gives us very specific signature, right? Um, Sorry. And then it actually goes to the vegetative period, and usually this, when you see this kind of signature, you know that it's actually paddy, right? So even sometimes simple models like that can be used. The most important thing is we also wanted to understand sowing and harvesting insights, right? So when a farmer decides to sow, right, the intent of sow, sometimes, looking at the current conditions, there's something called prevented sowing. The farmer might decide not to sow as well. That's also interesting, so that's prevented sowing. So for this particular region, we were looking at the peak time of sowing. So this is a cumulative, this is the cumulative graph, and this is the peak of the sowing, the number of farmers, acreages which is being sown. So we see that it somewhere starts in the month of October and it peaks like 1 month later, So some farmers might have seen that there is an early rain or something, right? And so they might have started sowing. But really most farmers' decision, of deciding to sow is around this. So we consider this as the peak time of sowing, So that's when, and you see that most of it is saturated. That means there are not many farmers who are still sowing, right? Similarly, like, harvesting as well. Harvesting is much more sudden, right? Like, you can see that, and usually sometimes, farmers might decide to harvest early because they want to prepare the land in advance for the next season also, so it's quite abrupt as well and quite sudden. So you can also see that, harvesting has also happened like, over a period of time, but after some time, it's just barren land, right? So you could look at one thing which we have observed from all of this analysis is that the time of sowing is like kind of like shifting, or the decision is being taken depending on the climatic conditions. One thing which we have seen is that the season itself is kind of like compressing. The crops are maturing very faster because it's accumulating heat very, very soon because of the climate change. So we see that the crops are, more vulnerable to the stresses, and so and sometimes they mature too quickly, and probably the quality is not as good as it used to be before. So the seasons are getting shorter, the quality is lower, right? And sometimes, we found that that led to also supply chain issues. Produce coming early than predicted into the market. And later on, when there was expectation that the produce, this happened, for example, for tomato last year uh, in Asia. And when later on, when the peak of the season, there was expectation, there was very less amount of produce, and that led to inflation, right? Um, okay, so this is the overall thing. So, just breaking it down, I think I talked a little bit about identifying, taking the satellite data, using ground truth data, And we look at the, how the land use and land classification is done. That means which are the regions where the crop is being grown. And then we, use a framework, which we have inbuilt to detect the crops, and as you can see that they are actually changing, right? Like different crops growing, different crops getting sown. And we want also to predict it at maturity, so we're doing this at scale across different geographies, and it's possible. And that's the advantage of doing this um, in for satellite data, right? Because it's easily scalable, because satellite data is available. In fact, publicly available satellite. All of this is publicly available satellite data that we use, right? It's medium resolution. It's not high resolution. It has its challenges, right? It cannot be used for precision agriculture. If you want to use for precision agriculture, then you really have to rely on high resolution satellite data, right? But not many people can rely on precision agriculture, on high resolution satellite data, right? Because it's very expensive. So what we did is we trained for some geographies, and then we, I'll not go into the details of this, but uh, we uh, we actually like infer and try to test it on other geographies as well, But this is something that we have been working on for quite a bit of time. Um, Now, so that's the crop identification framework, and on top of it, we do the yield estimation. But I'll come to that in a while, right? Um, but I also want to give an inspiration to this audience on also like where the whole of this, the whole of AI is kind of like moving towards also, right? And in this space, right? And not only vision, language, but satellite is also like not very different, right? And I want to give some inspirations of things that we are doing and hopefully inspire people also to look in that direction, right? So I've talked a little bit about the relevancy of data, the diversity of data, variety of data, and always like being fair about it, right? Equity and fair. Fairness is always something that we have to look at. And then the other thing which I talked about is also on explainability, right? Sometimes simple models are better than, and knowledge-based models are better than, purely data-driven approaches, right? So we tend to combine, both of the approaches in certain of the applications, data-driven and knowledge, combine them together, right? Or scientific models, science-based models, process models, combine them together, right? So that we call it as a hybrid model. Now, purely looking at it from data-driven approaches, like where the world is heading towards, right? And where, these are some recent inspirations and some recent work that, I just curated it for this particular webinar as well to give some ideas. Um, what happened is recently a lot of folks have been working on masked autoencoders, right? So, this encoder decoder kind of architecture is not kind of new. It's been there for a lot of period of time. The idea being that earlier it was used for purely for restoration, right? Like given an image, can you feed it? Can you just corrupt it? Can you feed it into an encoder, then feed it back into a decoder, right? And then get back the image, and how do you train that whole model into it, right? Recently, actually, like people started looking at this masked autoencoders. That means take an image, mask specific regions. There's a bird like a flamingo, right? So you take patches of it. You're only, these are the non-gray areas. The colored ones are the non-masked areas. The rest gray ones are the masked areas. You take those patches, you encode it, and then you create a decoder architecture. You get back the embeddings and then reconstruct the target, right? So the target is already available, and then you build the entire network, right? So this became like very useful for reconstruction for multiple different use cases, right? If you have like noisy data and how to do that. So satellite data also got inspiration from vision models and kind of did something similar. So you can look at this particular article. The references are given for both of this below. And it's very similar, right? You look at some encoding, position encoding, spectral encoding, right? But basically splitting this as masks, as patches, and then masking them, but doing it both in spectral or temporal direction, right? So that's the only difference. Okay. No, I have a an idea, and which I would like to propose, and this is an interesting idea, is that we have both optical and radar data. This is what we tried, and I'll show you some results from also that. We took that data and we intentionally corrupted it, right? And then we fed it to, we know actually what's growing, right? From ground labels, we know what's growing there and everything. But let's say that ground labels are not available and you feed this to an encoder and then decoder architecture, and you get back, how your real data looks like because I'm intentionally corrupting it. I can add some noise or I can mask them out, right? And I get my image. So I reconstruct them, right? So you can look at the latent space, and there are a lot of ways of modeling the latent space itself or not. But let's say that you have large amount of data set. You can look at it both from either vision, the convolution neural nets kind of approach, or patch-based approach like we talked about before, right? You can even consider the masking approach, what we talked before, as some kind of adding of noise, right? So you can just add like zeros everywhere here, and the rest of it is like you're just masking, you're just adding one, right? You're just multiplying it by one. So it's a kind of like noise which is added, right? So it's a masking approach. So, and this, my argument is that this actually system makes the model actually becoming great feature learner, okay? Earlier, I come from classical machine learning approaches. Earlier, if you want to have like, a specific task, you'd actually go and do wavelets or Fourier transforms and everything, build features, right? Like textural features, and things like that. And then you would build your classical machine learning model, such as support vector machines or random forests or whatever be it, right? And then do downstream tasks, right? Now, where the world is going into is that let's say that you have these corrupted samples, and then you're reconstructing them, then this guy here, the argument is that could be used for downstream tasks. And this becomes a great feature learner, right? And you don't have to do that. Now, we did this for, one region in Brazil, but this could be extended, in South America. So we took, a specific region. We took the satellite tile data. This is the optical data. This is the red, green, and blue channel, how it looks like. So there are like, some marshy regions, some croplands, there's some, forest area, So there is some crops growing here, some, and probably kept barren and things like that, right? We took this, the earlier approach that I took. I said, we intentionally took some satellite data, we corrupted them, we masked them and everything, and then we reconstructed them. We took this guy here out and, saw what is it that they have learned. So we gave it a new image, which is non-corrupted. We fed it inside and, we did a simple clustering approach on it, and you see that it's actually able to cluster them separately, right? In fact, you can give more number of clusters and make it more. I've given only 7 clusters, we have given only 7 clusters, but you could make more number of clusters and give more details to it, right? So this is kind of like unsupervised approach. So even without any labels, it's kind of getting some semantic representation, right? There are prior work on it, but this is our own work, right? We have not referred to anything. But you can take inspirations from this as well, is that in fact, so my earlier argument that, it's learning something, these features are learning. So I take these images and I take the features and then I do a clustering on it. You can do any kind of hierarchical clusters or k-means or whatever it is. And you actually find some relevant semantic segmentation happening here, right? So that's very interesting, and you can get as detailed, you can add more number of clusters, or you can group them together and everything, right? And you can bring also class labels to it. You can say that these are all similar classes versus other similar crops versus the rest of it is different, right? So that's one direction which is happening, So I want to give that as an inspiration because it's not necessary that you always need to have like supervised learning approaches, right? You can also have unsupervised learning approaches. So once we have identified crops, land, what's growing in the land, which areas is actually an active vegetation region where an active crop is growing, and once we have identified the crop, the next step is towards yield. So in the interest of time, I'll skip this, right? But it's actually looking at multiple different parameters, both remote sensing data and also weather data, and estimating the yield, right? you can actually estimate the yield, and you just need a minimal amount of crop related yield information, historical values in that location to actually give very reliable yield estimates. Right, and then we actually do the actual verification. So once we have estimated and everything, the most important thing is go down to the ground, go to those regions and find out, is there a crop growing, with permission, of course. Is there a crop that we detected? Is it growing? Is there then, you go and estimate also the yield and do some ground sampling, right? So we call that as CC, right? Crop cutting experiments, So these are some images from the field, like where you actually you go and measure the field, you crop that particular region, you cut it, and then you go and weigh it. You weigh the wet biomass, you dry it, and you weigh the dry biomass. You weigh the grain, if it is cob, you weigh the weight of the cob. And if there's some other grains, then you thresh them. Let's say if it's rice, you thresh them, and then you weigh the wet and the dry. After drying, you do that, right? So these are all validations that we do. So I'll just quickly, I'll just skip some of this and show some results from actual data from the sub-Saharan region. So we took all of that, overlaying we identified crops in a particular region, we estimated the yields, we do ground validation, right? So looking at, for example, this Kenyan and Nigerian regions, right? Like this is, IPC's, ASAL, the arid and semi-arid land, how it looks like, the distribution of it. Now, the interesting thing is that many of these regions are actually categorized as, emergency regions, right? Now, some of these maize growing regions, for example, West Pokot, Laikipia, Laikipia, sorry, and Baringo, earlier they were actually classified as stress, but this is an analysis that we did on climates. We find that these regions are actually moving into, from stress conditions to arid or, semi-arid or even arid conditions, So that's because by just plainly looking at the 20-year precipitation anomalies, right? 30-year precipitation anomalies against current precipitation as well. So I'll just show you how this looks on the grid. Okay. I hope my screen is visible. Okay, so this is this is looking at two different years, 2018 and 2023. Now this is grid level information, right? If you go, what we have done is each of this Kenya region we've divided into 5 by 5 kilometer grids, and so each of this grid, what it represents, red is where maize is growing, but the acreage within that maize acreage is about 0 to 350 hectares, right? And in the yellow one is so it's largely divided in terms of, it's just bucketed in terms of acreages where where there is lesser amount of acreage to actually very high acreage. So what you see in green, these are the regions where you actually have major maize growing regions. And even if you look at my first page, right, where I actually showed you the different agroclimatic zones, you see that these are mostly like the humid regions, right, where while these are some of these other regions are actually arid regions, even if you look at, for example, the Mandara County, these regions, they still have like, maize growing regions, but it's very sparse, right? And you can see that in each of this grid, it's very small, but there's a tooltip. It also shows how much of acreage is there, but how much of yield is there. Is the health above normal or below normal of the crop? Are there any climatic anomalies and things that, So you could go into much of the details in this as well. Going back to the slide, now what we did is we did for 2018 and 2023, and we did this study. Now the interesting thing that we found is that this Mandara region, which was already under heavy stress, we found that there is a shift in the crop acreages. So farmers are more moving towards the left, towards the west side, and in comparison to before, and one of the reason, which we attribute is because of non-availability of water for agriculture needs. Even in the areas where maize is a major production, we found that more than about 10% loss in production in 2023 versus 2018. So that's very significant. If you look at in terms of production itself, because these regions actually contribute a lot to Kenya's food availability. Not only that, what we see here is that many regions actually which were growing corn earlier, and now it actually disappeared. Many regions don't actually grow corn. So the black regions is areas where we no longer grow corn, and new regions emerge where green is where new acreages are getting established, new farm plots are getting established. Now, the thing is, even in those regions, for example, you can see that Nakuru, which was like earlier producing very high yield, which is in green, actually farmers decided not to grow for many multiple set of reasons, because the fertilizer production, fertilizer required cost is very high. And new regions, for example, there is actually, although it has new regions has come, but you see that a lot of them are red. Red means that, the yields are less than 1 ton per hectare, and that's very concerning. That means that farmers are moving to new locations, but the yield has not necessarily improved, right? So there are very few regions where, you actually see farmers have moved to new locations and yields have slightly increased, right? Maybe they've actually in this region where you have like slightly medium yields happening, which is a little bit higher than 1 ton per hectare. So the drop in production, like for example, we just took Kakamega and Nakuru, and I'll not go into the details of this, this is something called SPEI, the standard precipitation evapotranspiration index. It's what we found is that in these two counties, for example, there was almost 30% drop in production, and we attribute that to actually lower amount of rainfall. So what you see, for example, in these graphs is like, this purple one is in 2023, as against if you look at 2019, which is relatively a good year, cumulatively for all of these counties, because when we look at the county, it's not like one particular city or village or region. We, have to look at it in a cumulative way. The overall itself, it had been a good year for that that county, but you see that there is a tremendous amount of difference. So earlier it was extremely wet condition. Now it's actually extremely dry conditions, extreme drought conditions. So that's very concerning, So that's one of the reasons why Nakuru, which was earlier producing, a lot of was high yielding. Now, in fact, farmers decided not to sow, right? And so acreages have dropped. Okay. I'll just stop here for this particular country, and the rest of it is for the rest of the geographies, and I'll go into questions because I've also ran out of time. But what I also want to show is that, for example, in Bungoma County, like regions where neighboring urban populations, right? You see that there are regions where earlier this is like, giving an area of crop production in this area in 2018. Farmers decided not to sow. This is a baseline map. So baseline map doesn't change because it's from Google. Or you can take it from OpenStreetMap as well. But that doesn't change, right? But you see that this particular plot, they still have like some crop growing, right? The maize crop growing. But this large area the farmer decided not to sow in 2023. So that's very interesting. And you can also look at the the crop signatures as well, right? You can see that in this particular within the in 2018 versus 2023, it's kept barren, right? Oops, sorry, excuse me. So these are some news articles as well, which I wanted to share with you, where residents are actually moving into new regions. some regions where, for example, the temperature itself has risen. Kakamega, for example, it's risen by 1.5 degree. Okay, and because of that, it could be that the yield has dropped, right? And we could do many such kind of analysis. Now, yeah, sorry, I just have one last story, and before I'll stop, and I'll take questions. This is in Nigeria as well. Nigeria, we did a kind of like similar study for for wheat. And we found yield estimation, and we also did ground validation and everything, and we found that our yield estimation error rates are very minimal. But one thing which we found in this 13 states is this is a little bit older study, is that one particular region, especially which is the Borno state, we found that the yield of the acreages of the wheat crop had suddenly reduced, dropped. And in fact, like we got conflicting. Some people, said that it's not possible because this state is the largest wheat producer state in Nigeria. Now, Borno is actually like the northern part of Nigeria, the north eastern part, and that's actually a conflicted region, and it's one of the region which was actually affected by insurgency, and farmers' migration had actually happened. So because of geopolitical conflicts, also the farmers decided not to sow. So the acreages fell down very, very significantly, right? So there are some extensions globally as well. So this is right across, our own backyard. This is actually in Glenn County in US, where we are looking at rice production. Many farmers, what you see in blue, which were 2021, they were sowing. It's actually like high soil moisture content. In 2022, there was like very less or almost drought conditions, and farmers decided not to sow. For example, in 2021, these are identified regions of paddy. In purple, these regions don't have paddy anymore. In fact, Glenn County had 63% drop in rice acreages. Similarly, we have done for India as well, where we are looking at, temperature, extreme temperatures, and, yield effects of yield on wheat crop and things like that, right? So I'll stop here, and, I'll maybe like walk in through the questions, and because this probably, gives an idea of also other questions that came in regarding the extensions to global geographies as well. So it was very important to address that. I'll address the first question first. How does the regional historical crop production and yield data blend in with any data source, right, that is generated? So that's a great question. In fact, the best way to do that is historical data, either at acreages, could be used to kind of like fine tune the model as well. Like if those are available historically, then it's good because you also use that as a basis to kind of look at, where you're doing well, where not doing well. In fact, if it is available more at plot level, then it's much more better, right? Because it's always difficult to look at aggregate level data sources, right? In fact, some of these, when we are looking at regional level, in fact, we do look at knowledge coming from multiple different departments and universities and even farmers' knowledge. We look at yield, right? In fact, we take actually, inspiration and also knowledge from multiple different scientific data sources in a particular region. Often, if no information is available, we have to rely on that, right? So we do actually get that information as well, and then we fine tune our yield models on top of it, right? And is there any way to add, land surveys and everything as well? Right, and that's a really good question as well. In fact, like in many with working with the governments also, we tell them that these are recommendations that we could actually identify regions which have like where this particular crop is growing, and in fact some of the regions farm boundaries are indeed captured in some of these surveys, right? But sometimes it's kept private for confidential reasons, so it's not publicly disclosed. So it's possible to, add, if government wants, they could add these intelligence on top of it and also see if they need to provide advisories for farmers, right? So that's really is possible because we take that regional intelligence and then you can overlay it on top of these farm or plot boundaries, and provide that back. And in fact, that's a very important thing to do, right?
So if I may, I'm actually seeing that a couple questions here are asking about climate change, but also severe weather events. You mentioned drought. Some of these things come, the time scale of climate is, both very long and very short. And when you're thinking about extreme weather events like drought or like hurricanes, like, rainy season, how do you think about the uncertainty that injects into your models?
Yeah, that's a great question. So what we, you know, in fact, when we actually study the land, right, we study the actual data that's coming from visible from satellite data, right? And so that factors in, so if there are any uncertainties with respect to weather in that region, the crop will respond, and any response that we see, then we actually can actually get that back in, right? We see that on the satellite through the satellite data, right? So any stresses or any drop in the parameters that we're observing, we see that's already kind of like giving out a red signal for us. What is currently challenging is, and I think that's where probably forecast models have to be built. There are different kinds of scenarios, right? Like, for example, if there is a hurricane or extreme wind event that happens, right? Like, let's say that there is an extreme wind event that happens tomorrow or day after tomorrow, then all your crops can actually get like wiped out, right? Like so there's something called lodging which can happen, and that can actually lead to crop losses, right? So that has to get more precise. Even as we speak, there are multiple different forecasting models and even nowcasting models which are available. So if those forecasting models become more reliable, now there is a lot of uncertainties. The more you move away from longer duration that is there, let's say a week or 2 weeks later, they become more uncertain, right? But you could factor those in. There might be extreme wind events or extreme flood events that might happen, extreme rain anomalies precipitation anomalies that might happen. So then potentially, the farmer could incur a loss, right? Those are things which we could also bring in, right? And those we send out as alerts in case, extreme event happens, we send that out as farmer alerts. I hope that addressed your question.
Well, thank you. And thank you for your time. And thank you everyone for all your questions. This has been a really incredible session. Before we close, I'd like to mention that our next industry seminar will be on March 21st at 1:30 with Ron Popka of Voya Investment Management. Registration is available on our website, datascience.harvard.edu, and through our weekly newsletter. And we hope to see folks there. Thanks once again. Thank you, Praveen, for such a thoughtful talk, and it's generated so many questions. Thank you, everyone, for your questions and your engagement. Recording will be available soon. Take care, everyone.
Thank you.
Thank you very much.
Yeah.